What about chemical reactions? Now, we've been looking at boiling or melting. Those are physical changes. What about chemical changes? Okay. We can compare if we talk about independent states. All right, so here we have N2 gas plus 3H2 gas goes to 2NH3 gas. We should expect a decrease in entropy. Why? Why does this reaction have a decrease in disorder or an increase in order? Well, if we talk about possible positions, if we have 4 moles of gas on the left but only 2 moles of gas on the right, we have fewer particles. If you have fewer particles, there's fewer positions those particles are going to occupy. So that's an increase in order or a decrease in disorder, which means a negative value for delta S. Okay. What about this one? 4NH3 plus 5O2 goes to 4NO plus 6H2O. What would we expect our delta S to look like here? Well, again, we have single state here, so gas on one side, gas on the other. On one side, we have 9 moles of gas. On the other side, 10 moles of gas. So as this reaction proceeds in the forward direction, we have more molecules to take up more positions, which means we have more disorder. So predict the sign of delta S for the following reactions. Solid calcium carbonate decomposing into calcium oxide and carbon dioxide. Would we see a positive delta S or a negative delta S? Increasing disorder, right? Positive delta S. We're producing, taking a solid, very ordered, and we still have a solid, but with them we also have some molecules of gas. It's more disorder. How about this one? 2SO2 gas plus O2 gas goes to 2SO3 gas. Look at the moles of gas on one side and the moles of gas on the other. We should be decreasing disorder because we're producing fewer particles. It means fewer positions. So there are actual S values for substances. Okay. Normally we deal with delta S, but actual S values exist. The third law of thermodynamics allows us to do this. The third law of thermodynamics says that at absolute zero, 0 Kelvin, remember, 0 Kelvin is a temperature at which there is no kinetic energy, zero movement. If a particle can't move at all, then it can't occupy any other positions. So the law of thermodynamics, the third law, tells us that at absolute zero, a perfect crystal has an entropy of 0. It's the only time entropy will be 0. That means that that's a standard, and that means we can measure all other entropies at all other temperatures against that. Okay, all S values will be positive because as long as they're above 0 Kelvin. So all S values will be positive as long as they're above 0 Kelvin. Appendix 4 in your book has some common entropy values for common substances at 298 kelvins and 1 atmosphere, which is thermodynamic standard states. Okay, and all we have to do, since S is a capital letter, it's a state function, we can find delta S by subtracting final minus initial. It's the summation law, we should be very familiar with. So let's take a look at an example. Here's a reaction between nickel 2 sulfide and oxygen to form SO2 and nickel 2 oxide. The numbers underneath each of those substances are the S values from the appendix. Since we're looking for delta S standard, that's what the degree sign means, we have to use standard values, and those are the ones that are in the appendix. Okay, so we're going to use the summation rule to figure out delta S for this reaction. Okay, we use the summation rule. That means that we calculate the total entropy of the products, so 2 times 248 for the SO2, 2 times NiO for the NiO, the 2 times 38, and then we subtract from that 2 times 53 for the 2 NiS, and 3 times O2 for the 2O5. And you'll notice that elements don't have a 0 value for entropy because all substances have a positive value for entropy as long as they're not at absolute 0. Okay. The last thing we'll take a look at is free energy and chemical reactions. Okay, so the standard free energy change. Standard, remember, standard is represented by that little degree sign, and it means that reactants and products are at standard states. That's 298 kelvins and 1 atmosphere. We can't measure delta G directly, but we can calculate it from other measured values. There's 3 ways to do it we're going to take a look at. Standard states are listed in page 260 in the chart if you want to review those. Remember, once we know what delta G is, the more negative it is, the more we know that reaction is shifting to the right. It's more spontaneous. And if it's a 0, then we're at equilibrium. So the three ways to calculate delta G. The first way is to use our equation, delta G is equal to delta H minus T delta S. When would you use this? Well, if you're given delta H formation values or S values from the appendix, then you have to do it this way. Okay, you're going to have to calculate delta H by doing products minus reactants for the HF values, and the same thing for delta S, and then you plug it into the equation. Okay. You can use Hess's law. When would you use Hess's law? Well, if you're given equations and some delta G values for each of those equations, you can rearrange the equations, flip them around, multiply through, cross things out, and then add them together to get the goal equation. And then you can add up the delta G values for the equation. Remember, if you flip an equation around, you have to change the sign of it. If you double it, double the coefficients, you have to change the value of delta G. We treat it just like we do any Hess's law problem. The third thing you can do is you'll notice in Appendix 4, there's a column that says delta GF. Those are the standard free energy of formation values for each substance. And we can use them just like the enthalpy of formation values. We can do the products minus reactants, add them up, and we can get the delta G for reaction for that in that way. So depending on what data you're given, you may have to use one, or sometimes you can use more than one of these values. But usually a problem will give you the data so that it forces you to use one of these three ways. But it's not that difficult. Just kind of evaluate and then choose one of the three ways to do it. You get some practice doing this.